Imagine looking up at the night sky and seeing not one sun, but seven all tangled together in an intricate cosmic ballet. What sounds like science fiction is actually one of the universe's most breathtaking realities: septuple star systems. These stellar families, where seven individual stars are locked in an eternal gravitational dance, challenge everything we thought we knew about how stars form, interact, and even how planets might survive in such extreme environments. For decades, astronomers believed that binary or triple star systems were as complex as it could get, but the discovery of systems with seven suns has rewritten the textbooks and opened up a whole new frontier of cosmic mystery. What makes these systems so captivating isn't just their sheer number of stars, it's the bizarre and often outright strange phenomena that occur within them. From stars that seem to defy the laws of physics to planetary orbits that look more like abstract art than stable paths, septuple systems are a treasure trove of astronomical oddities. Some of these stars are so close they exchange material in a slow-motion stellar tango, while others are so far apart that their gravitational bonds seem impossibly fragile. And then there are the planets' worlds that experience multiple sunrises and sunsets, where the sky might be lit by a kaleidoscope of different colored suns, some blazing hot and others faint and cool. How can such delicate arrangements persist across billions of years? What can they teach us about the formation of stars, the birth of planets, and perhaps even the possibilities for life in the most extreme corners of the cosmos? In this video, we're going to explore 30 of the most astonishing discoveries ever made about septuple star systems. We'll journey from the deeply theoretical to the mind-bendingly observational, uncovering secrets about stellar formation, orbital dynamics, and cosmic evolution that continue to baffle and inspire astronomers. You'll learn about stars that shouldn't exist, planetary orbits that defy logic, and the incredible tools and missions that have allowed us to peer into these complex celestial families. So settle in, stay curious, and get ready to see the universe in a whole new light, because the story of these seven sun systems is stranger and more spectacular than anything we could have imagined. Our journey into the strange begins with the system that started it all, Cassiopeiae. For a long time, astronomers had classified it as a fairly standard, though bright, multiple star system. But as our technology and understanding grew, so did the mystery of Cassiopeiae. Detailed spectroscopic observations began to reveal that what we thought was one star was actually two, locked in an incredibly tight orbit. And then further analysis showed that those two were gravitationally bound to another pair, and then another, until, piece by painstaking piece, a monumental picture emerged. Not two, not four, but seven distinct stars, all bound together in a single, sprawling system. The architecture of this stellar family is what truly boggles the mind. At its heart is a spectroscopic binary. This is a pair of stars so close together that not even our most powerful telescopes can resolve them as two separate points of light. We only know they are two because of the Doppler shift in their light. As they whip around each other, their light waves stretch and compress, revealing their frantic orbital dance. This central pair is then orbited by another binary system, and then another, creating a hierarchical structure that resembles a celestial set of nested Russian dolls. It's this precise gravitational ordering that keeps the entire system from tearing itself apart. The existence of such a complex arrangement forces us to rethink the very process of star formation. We used to think that the chaotic collapse of a stellar nursery would make a system with more than 3 or 4 stars inherently unstable, destined to break apart. Cassiopeiae stands as a defiant counterargument. It proves that under the right conditions, a vast cloud of gas and dust can fragment and collapse into a stable, multi-tiered system that can endure for billions of years. It's a masterpiece of gravitational engineering, a natural wonder that has become the foundational example for understanding all high-order multiple systems. While Cassiopeiae is a model of gravitational stability, Nu Scorpii presents the complete opposite, a stellar system in a state of near-constant chaos. If one system is a meticulously ordered clockwork, the other is a spectacular, unpredictable demolition derby. This collection of 7 stars doesn't follow the neat, hierarchical rules we see elsewhere. Instead, its members are locked in a dramatic and unstable gravitational dance where their highly elliptical or egg-shaped orbits bring them perilously close to one another before flinging them back out to the far reaches of their shared space. These aren't the gentle, predictable ellipses of our solar system's planets. The orbits in Nu Scorpii are so extreme that astronomers use the term dynamic instability to describe them. This means the gravitational interactions between the stars are so strong and complex that their paths cannot be perfectly predicted far into the future. A near miss between 2 stars can drastically alter the orbit of a third, sending it on a new trajectory that will itself influence another star decades or centuries later. It's a cosmic chain reaction of gravitational billiards playing out over immense timescales. The most dramatic consequence of this chaos is the potential for stellar ejection. During these close encounters, the complex interplay of gravitational forces can accelerate one of the stars to a tremendous speed, providing it with enough energy to escape the system's gravitational pull entirely. This process, poetically known as gravitational slingshotting, might be how many lone rogue stars wandering the interstellar void were born. They were kicked out of their chaotic birth families long ago. In Nu Scorpii, we are essentially watching a slow-motion version of this stellar eviction process, a natural laboratory for studying how star systems can lose their members. This relentless gravitational turmoil also has a profound effect on the stars themselves. The immense tidal forces generated during a close pass can literally stretch and compress a star, heating its outer layers and potentially triggering unusual flare activity or altering its life cycle. For any hypothetical planets that might have formed in this system, the environment would be apocalyptic. Their orbits would be constantly shifting, their skies filled with multiple, chaotically moving suns, and their very existence would be under constant threat from a gravitational upheaval that could fling them into the frozen depths of space or directly into a star. Nu Scorpii doesn't just challenge our understanding of stellar mechanics. It showcases the universe's raw, untamed power to create breathtaking chaos within a family of stars. Moving from the gravitational chaos of Nu Scorpii, we find a different kind of mystery in a system known as HD 98800. For a long time, this system was catalogued as a relatively straightforward quadruple arrangement, complex but understandable. Yet, as with so many of these cosmic families, closer inspection revealed that its story was far from complete. Astronomers began to detect subtle gravitational nudges within the system, the kind that hinted at the presence of more members, potentially pushing the total count to 7 and placing it firmly in our category of septuple stars. But the most captivating clue isn't another bright star, it's something that can't be seen at all. This is the mystery of the dark companion. Precise measurements of the orbits of the known stars show they are ever so slightly wobbling, as if being gently tugged by an unseen partner. This invisible object has mass enough to exert a clear gravitational influence, but it emits no detectable light across the electromagnetic spectrum. It is a true ghost in the celestial machine, and its nature is one of the most engaging puzzles in the study of multiple star systems. So what exactly is this dark, massive object? Astronomers have several compelling theories, each more fascinating than the last. The first candidate is a brown dwarf. Often called failed stars, brown dwarfs are objects that formed like stars but never gathered enough mass to ignite sustained hydrogen fusion in their cores. They can be vastly larger than Jupiter, yet glow only faintly with the residual heat from their formation. making them incredibly difficult to spot against the brilliant backdrop of other stars. Another possibility is that the dark companion is a super Jupiter, a planet so enormous it blurs the line between planet and brown dwarf. If this is the case, its existence raises profound questions about planet formation. How could a planet that massive form or survive in such a complex gravitational environment? Its mere presence would challenge our models, suggesting that planetary birth in these extreme systems is not only possible but can sometimes produce veritable giants. And then there's the most exotic possibility, a stellar mass black hole. While it may sound like science fiction, it's a viable candidate. A small black hole, the remnant of a dead star that went supernova, would have exactly the properties we observe: significant mass, zero emitted light, and a powerful gravitational pull. If confirmed, this would mean the Septuple system isn't just a family of stars. It also contains the ghost of a star that once was, a silent gravitational anchor from a past cataclysm. The presence of such a dark object completely transforms our understanding of the system's dynamics and history. Its gravitational influence acts as a hidden architect, subtly shaping the orbits of the visible stars over immense periods of time. It could be the key stability factor, preventing the entire system from flying apart, or it could be a source of long-term instability. Its unseen tugs slowly altering trajectories in ways we are only beginning to model. This discovery forces us to acknowledge that what we see in the cosmos is often only a fraction of what's truly there, with dark, massive objects lurking unseen, reminding us that the universe still holds its secrets closely. But if mature systems like Cassiopeiae and chaotic ones like Nu Scorpii represent the later chapters in a star's life, there exists an even more profound window into the origins of these cosmic families, the stellar nursery. Here, in the dense, swirling clouds of gas and dust where stars are born, we find septuple systems in their infancy. These are not the stable, hierarchically ordered structures we see elsewhere. They are raw, protostellar embryos, and they are revolutionizing our understanding of how multiple stars form together. The key players in these newborn systems are known as T-Tauri stars. Named after the prototype star found in the Taurus constellation, these are stellar infants, often just a few million years old. To put that in perspective, our own sun is 4.6 billion years old. These T-Tauri stars are cosmic toddlers, still glowing hot from the immense energy of their gravitational collapse. They haven't yet begun the process of nuclear fusion in their cores. That final step to becoming a true main sequence star is still millennia away. Instead, they are slowly contracting, settling into their final form, often surrounded by a swirling disk of leftover material from which planets might one day coalesce. Finding a system of 7 T-Tauri stars all bound together is a discovery of monumental importance. It provides a snapshot of the very process of multiple star formation, frozen in time. It strongly suggests that these complex families aren't the result of random captures or chaotic mergers later in life. Instead, the entire septuple system was born together, all originating from the same single, massive cloud of gas and dust. The prevailing theory for how this happens is called turbulent fragmentation. Imagine a vast, turbulent cloud begins to collapse under its own gravity. As it shrinks, it doesn't do so smoothly. Instead, internal ripples, rotations, and pockets of higher density cause it to break apart into several smaller clots. Each of these clots continues to collapse, forming its own protostar. In the case of a septuple system, this fragmentation process happened not once, but across multiple scales, creating a nested hierarchy of stellar seeds all at roughly the same time. Observing a young septuple system is like finding a group of siblings still in the maternity ward, providing direct evidence for this theoretical birth process. These young systems are also incredibly dynamic and chaotic environments. The protoplanetary disks around each star can interact, potentially feeding material to one another or even colliding. The stars themselves, still settling into their orbits, may migrate inward or outward, their gravitational interactions shaping the system's future architecture. It's a violent, messy, and energetic nursery, but within that chaos lies the blueprint for the stable or wildly unstable systems they may become billions of years from now. By studying these youthful septuples, we are essentially watching the universe in the act of building some of its most complex and breathtaking structures. Now, within the intricate architecture of these septuple systems, we encounter one of the most extreme and intimate relationships stars can have, the overcontact binary. Picture two stars locked in such a tight, close embrace that their outer atmospheres aren't just touching, they've actually merged into a single, common envelope of gas. These stellar partners are so profoundly connected that they literally share their material, creating a dumbbell or peanut-shaped structure spinning through space. Finding such an intense, volatile pairing at the heart of a system with 7 stars is like discovering a hyperactive engine driving the entire cosmic machine. The existence of an overcontact binary fundamentally changes the rules of the game for the entire system. This isn't a stable, predictable dance, it's a relationship defined by constant, dramatic exchange. Hydrogen, helium, and other stellar material continuously flow from the more massive star to its less massive companion, a process that completely alters the fate of both stars. The donor star loses mass while the gainer star grows heavier and spins faster. This transfer of mass directly impacts the star's life cycles, often causing them to evolve in ways that completely defy the standard solitary star models we rely on. This relentless flow of material doesn't just affect the binary pair, its consequences ripple outward, influencing every other star in the gravitational web. The mass transfer changes the central gravitational anchor of the system. As the binary pair loses and gains mass, their combined center of gravity shifts. This sends subtle but persistent gravitational waves through the entire septuple arrangement, forcing the other 5 stars to continuously adjust their orbits in response. It's a domino effect on a cosmic scale, where a change in the core dictates the motion of the entire family. This ongoing instability opens the door to some of the most cataclysmic events in the universe. The transferred material can accumulate on the surface of the gainer star, and if enough hydrogen builds up under intense heat and pressure, it can ignite in a runaway thermonuclear explosion. From our vantage point, this would appear as a nova, a sudden, dramatic brightening of the system that could last for weeks or months. In a septuple system, such an eruption would momentarily outshine all the other stars combined, flooding the surrounding space with radiation and potentially disrupting the delicate orbits of any forming planets. The most dramatic final act for an overcontact binary, however, is a full merger. The relentless transfer of mass and angular momentum can slowly drag the 2 stars closer and closer together until their cores finally coalesce. In a final, brilliant flash, they would become a single, rapidly spinning and massively enlarged star. For the rest of the septuple system, this would be a moment of profound upheaval. The sudden change in the central mass would be like cutting the central string in a mobile. The entire gravitational balance would be thrown into chaos, potentially triggering a cascade of new orbital arrangements or even ejecting one or more of the other stars from the system entirely. The presence of an overcontact binary means the system is not in a steady state. It is a dynamic, evolving entity with a potentially violent future. You would naturally assume that the gravitational pandemonium of 7 stars would turn any surrounding space into a no-go zone for planets, a chaotic region where the very ingredients for world building would be scattered to the cosmic winds. Yet, the universe loves a good paradox, and septuple systems like HD 98800 are here to deliver it. Within this gravitational labyrinth, astronomers have found something that should not exist: vast, massive disks of dust, rock, and ice, the very raw materials from which planets are forged. These are not the smooth, serene rings of Saturn. These are debris disks, chaotic and warped construction zones that tell a story of resilience and gravitational artistry. The existence of these disks is a testament to an incredible cosmic balancing act. They exist within the system's habitable zone, the region around a star where temperatures are just right for liquid water to exist. In a single star system like our own, this is the prime real estate for planet formation. But here, with 7 gravitational masters vying for control, this zone becomes a place of extreme and fluctuating forces. The debris within it is constantly being jostled, heated, and pulled by the competing tugs of the stars, creating a disk that is anything but flat and calm. Instead, it's warped, twisted, and full of complex structures, spiral density waves, clumps of material, and vast gaps cleared by the unseen hand of gravity. These bizarre shapes are a direct map of the gravitational forces at play. The competing pulls from the various stars create regions of stability and instability within the disk. In some areas, their gravity cancels out, creating peaceful havens where dust particles can gently collide and stick together, the first step in building a planetesimal. In other areas, their gravitational tides align, creating powerful resonances that either stir the material into a frenzy or sweep it clean entirely, carving out empty lanes in the disk. Observing the structure of a debris disk in a septuple system is like reading a forensic report of the gravitational battles happening around it. This leads to the most thrilling possibility hinted at by these disks, the existence of planets themselves. Could a world actually form and survive in such an environment? The presence of a massive debris disk suggests that the planet-building process is not only possible but might already be underway. The constant collisions within the disk, while disruptive, also provide the energetic encounters needed for small particles to accrete into larger bodies. It's a violent and inefficient process compared to the calm of a single-star nursery, but it is a process nonetheless. Any planets that did manage to form here would experience a reality beyond our wildest imagination. Their orbit would not be a simple ellipse around a single sun. It would be a complex path dictated by the combined gravity of 7 different points of light. They might loop around one binary pair while being gently tugged by another pair much further out, tracing a stable, if incredibly complex, path known as a circumbinary orbit. The sky from such a world would be a perpetual spectacle filled with multiple suns of different colors and brightnesses, some locked in a tight dance with each other, others appearing as distant, brilliant stars. Day and night would be irregular concepts with periods of multiple sunrises and sunsets, and perhaps even times of perpetual daylight when several stars are above the horizon. The very definition of a year would be almost meaningless, a simple number incapable of capturing the intricate celestial mechanics governing its journey. Finding a debris disk in a septuple system doesn't just challenge our theories, it expands our concept of what a planetary system can be, proving that even in the most extreme gravitational environments, the persistent forces of accretion and stability can still, against all odds, build new worlds. This extraordinary interplay of gravitational forces leads us to one of the most dramatic events a septuple system can experience, the stellar slingshot. Within these densely packed families, the immense gravity of each star acts as both a tether and a catapult. When the complex orbital dance brings 2 stars exceptionally close together, their gravitational interaction isn't always a gentle nudge, it can be a violent exchange of energy. One star might absorb orbital energy from the other, dramatically accelerating as it swings around its sibling in a maneuver that mimics the gravitational assist we use to propel our own spacecraft across the solar system. But on a stellar scale, the consequences are far more extreme. The star that gains this immense kinetic energy doesn't just shift to a slightly larger orbit, it can achieve escape velocity. In a flash of cosmic violence, it breaks free from the gravitational bonds of its entire family, hurled out into the void of interstellar space. This is the birth of a runaway star, a stellar fugitive ejected from its home and set on a one-way trip across the galaxy at breathtaking speeds, often exceeding hundreds of thousands of kilometers per hour. We don't have to witness these ejections directly to know they happen. The evidence is written in the motion of the stars themselves. Astronomers have traced the paths of these lonely, high-velocity stars backwards through the galaxy, and in several remarkable cases, those paths lead directly back to known septuple systems. It's like finding a single, speeding bullet and tracing its trajectory back to the gun that fired it. These solitary runaways are the smoking gun, the permanent record of a gravitational upheaval that occurred millions of years ago. The departure of one star doesn't just create a cosmic runaway, it fundamentally rewrites the history of the system it left behind. The sudden loss of a significant amount of mass creates a massive gravitational imbalance. The remaining 6 stars, which had spent eons settling into a stable or chaotically stable arrangement, are suddenly thrown into disarray. Their orbits must reconfigure, shifting and adjusting to fill the gravitational void. This can lead to a new era of instability, potentially triggering further ejections, or it might allow the system to settle into a more stable, less crowded hierarchical structure. A single slingshot event is a pivotal moment that echoes for millions of years, permanently altering the destiny of an entire stellar family. While the gravitational dynamics of these systems paint a picture of cosmic chaos and order, the stars themselves hold a hidden, chemical record of their interactions written in light. When astronomers point their spectrographs at the individual stars within a septuple system, they aren't just measuring their motion, they're taking a detailed chemical inventory of their atmospheres. And what they often find is deeply strange. Certain elements like lithium or barium appear in abundances that completely defy expectation. In a normal, isolated star, lithium is quickly depleted early in its life, consumed by nuclear reactions in its hot interior. Finding a star with a lithium overabundance is like finding a pristine, uneaten meal in a busy kitchen. It suggests something unusual has happened to preserve it or deliver it anew. These peculiar chemical signatures are the smoking gun of a process called mass transfer. In the incredibly tight orbits of an overcontact binary or during a close gravitational encounter in a chaotic system, material from the outer envelope of one star can be stripped away and captured by its companion. This isn't a gentle process, it's a stellar theft where one star donates part of its very being to another. The captured material doesn't just vanish, it settles onto the surface of the receiving star, effectively polluting its atmosphere with a new chemical composition. If the donor star was enriched with certain elements, those same elements will now appear as an anomalous overabundance on the receiver. A barium-rich giant star transferring material to a smaller companion, for instance, would create a star with a bizarrely high barium signature that its own nuclear processes could never have produced. This makes each chemically peculiar star a fossil record, a celestial artifact preserving the evidence of a past violent interaction. By reading these elemental signatures, astronomers can work backwards to reconstruct events that may have occurred millions of years ago. They can determine which stars have interacted, estimate how much material was exchanged, and even gauge the ferocity of the encounter. This turns the entire septuple system into a living crime scene, where the chemical evidence on the stars allows us to piece together the history of their gravitational relationships, revealing a narrative of theft, survival, and transformation that is otherwise invisible to our telescopes. Hidden within the intricate light patterns of these 7 star systems is a celestial clockwork so precise it allows astronomers to take the universe's measurements. This is the phenomena of the eclipsing binary, a pair of stars whose orbit is perfectly edge-on from our perspective here on Earth, causing them to periodically pass in front of one another. Each time this happens, the combined light of the system dips in a predictable, telltale rhythm. A single eclipsing binary is a gift to science, but finding one nested within a septuple system is like discovering a master key. It unlocks a deeper level of understanding for the entire cosmic family. The true power of these eclipses lies in the data encoded within the dip of starlight, known as a light curve. When the smaller star moves behind the larger one, we get a primary eclipse and a significant dip in brightness. When the smaller star passes in front of its larger companion, it blocks a smaller portion of the light, creating a secondary, shallower dip. The precise depth, duration, and shape of these dips are a treasure trove of information. They allow astronomers to calculate the exact sizes of the stars relative to each other with incredible accuracy. The timing between eclipses gives the orbital period, and when combined with velocity measurements from spectroscopy, it reveals the star's masses, the most fundamental property of any celestial object. But in a system with 7 stars, this clean, elegant signal is thrown into a symphony of light and shadow. Imagine trying to listen to a single violin in an orchestra where every musician is playing a different song at once. That's the challenge faced by astronomers. The clean, predictable light curve of the central eclipsing binary is now superimposed with the light of 5 other stars. Their constant, combined glow forms a bright and fluctuating background against which the eclipses must be detected. Furthermore, if any other pair of stars in the system also happens to be in an eclipsing configuration, their own independent dips in brightness will overlap with the first, creating a fantastically complex pattern of dimming and brightening that looks more like abstract art than a clean dataset. Untangling this knotted web of light requires more than just patience. It demands some of the most sophisticated computational power and algorithms on the planet. Astronomers employ a technique known as Fourier analysis, which acts like a cosmic filter, mathematically decomposing the complex light signal into its individual rhythmic components. It can identify the distinct periodicities of each potential eclipsing pair hidden within the noise. Once these signals are isolated, complex modeling software takes over, creating a digital twin of the entire septuple system. Scientists can then virtually adjust the sizes, masses, temperatures, and orbital tilts of every single star, running thousands of simulations until the virtual light curve produced by the model perfectly matches the actual observed data from the telescope. The payoff for this immense effort is nothing short of revolutionary. By precisely characterizing the eclipsing binary, we anchor our understanding of the entire system. The accurately measured masses and sizes of those 2 stars become fixed points in our model. Their gravitational influence is now a known quantity, which allows us to far more accurately calculate the masses of the other 5 non-eclipsing stars by observing how they respond to its pull. This transforms our entire model of the system from an educated guess into a precise, quantitative map. We move from knowing that 7 stars exist to knowing exactly what they are, how big they are, and how they move. It's through this meticulous process of decoding starlight that these distant, chaotic families become known to us, one eclipsing dance at a time. And now we arrive at one of the most profound and eerie possibilities within these stellar families, the presence of a ghost. In a handful of septuple systems, the precise mathematical dance of the 7 visible stars contains a subtle, yet undeniable anomaly. Their orbits wobble. Their paths are ever so slightly perturbed, as if an unseen hand is gently tugging at them. This gravitational fingerprint points to the existence of an 8th hidden body of immense mass. But this object emits no light, no radio waves, no radiation that our telescopes can detect. The most compelling explanation is that we are not just looking at a system of stars, but at a system that also contains a stellar mass black hole. The method of this discovery is a testament to the power of indirect observation. Astronomers cannot see the black hole itself, instead they detect its influence. By meticulously mapping the orbits of each star over years or even decades, they can calculate the precise gravitational forces required to produce those paths. The math reveals a glaring inconsistency. The combined gravity of the 7 known stars is insufficient to account for the observed motions. There must be an additional source of gravity, a massive, dark object whose pull is essential to the system's current architecture. It's like listening to a complex piece of music and hearing a deep, resonant note that none of the visible instruments are playing. The concept of a supernova occurring within such a tightly bound system without utterly destroying it is a staggering thought. A supernova is one of the most violent events in the universe, capable of flinging material outward at a significant fraction of the speed of light. For a black hole to be present, a massive star must have lived its life and died in this explosive fashion. The fact that the other 6 stars remained gravitationally bound after such a cataclysm suggests the original progenitor star was likely the outermost member of the system. Its death may have occurred asymmetrically, with the supernova kick acting like a carefully placed thrust that ejected most of the star's mass but left the dense core, the newborn black hole, in a stable orbit. Alternatively, the system may have been so hierarchically stable that the gravitational bonds of the inner stars were simply too strong to be broken, absorbing the violent shock and recalibrating their dance around their new dark anchor. This dark companion would fundamentally alter the system's long-term evolution and stability. A black hole acts as a gravitational anchor of immense power, its influence felt across vast distances. Its presence could be the very reason the system has held together for so long, its powerful gravity acting as a stabilizing force that prevents the other stars from drifting apart or ejecting one another. Conversely, it could be a source of perpetual chaos. Any star that ventures too close on its elliptical orbit could have its outer layers stripped away by the black hole's tidal forces, creating a swirling, superheated accretion disk that would periodically light up the system with intense X-rays. The black hole doesn't just share space with the stars, it actively participates in the gravitational symphony, composing a deep, dark bassline that dictates the tempo for everything else. The gravitational tides that weave these 7 star families together do more than just dictate their paths. They fundamentally change the very nature of the stars themselves, spinning them up to velocities that would be unthinkable for a solitary sun. In the serene isolation of deep space, a star like our own rotates at a leisurely pace, its equator completing a full turn roughly once every 27 days. But place that same star into the chaotic gravitational field of a septuple system, and it can be whirled into a frenzy, spinning so fast its equator might streak around in a matter of hours. This isn't a gentle push, it's a stellar transformation driven by the relentless transfer of energy from the complex orbital dance directly into the star's own spin. The primary engine for this spin-up is the same mechanism that drives the oceans on Earth, tidal forces. When 2 stars orbit closely, the gravitational pull of each creates a tremendous tidal bulge on the other, much like the Moon pulls on Earth's oceans. In a stable, circular orbit, these bulges can remain locked in place. But in the eccentric, elliptical orbits common in these complex systems, the story is different. As the stars swing closer together and then further apart, the angle and strength of the tidal pull change constantly. This varying force acts like a rhythmic push on the star's bulge, effectively pumping energy into its rotation and causing it to spin faster and faster over millions of years. It's a cosmic version of pushing a child on a swing at just the right moment to make them go higher and higher. The consequences of this rapid rotation are dramatic and visible across the electromagnetic spectrum. A star spinning at such a breakneck velocity becomes a hotbed of magnetic activity. Its internal dynamo, the churning plasma deep within that generates its magnetic field, is supercharged. This results in a star that is effectively covered in massive, tempestuous starspots, regions that are cooler and darker than the surrounding surface, but often the source of colossal eruptions. Flares from such a star would dwarf anything our Sun produces, unleashing torrents of X-rays and ultraviolet radiation that would periodically bathe the entire system. Furthermore, the star's magnetic field gets wound up tighter, funneling charged particles off its surface and accelerating them into space, creating a stellar wind of such ferocity that it can strip away the atmospheres of any nearby planets and visibly eat away at the outer layers of a close binary companion. In the most extreme cases, this rapid spin doesn't just create activity, it begins to distort the star's very shape. The immense centrifugal force generated at the equator literally fights against gravity's pull, causing the star to bulge outward. What was once a sphere begins to flatten, taking on the shape of a pumpkin or a rapidly spinning top. There exists a theoretical limit known as the breakup velocity, where the centrifugal force at the equator exactly equals the force of gravity. If a star is spun up to this critical point, it can no longer hold itself together. Material at its equator will be flung off into space, forming a tenuous but permanent ring of hot gas, a stellar version of Saturn's rings, or a disk that might eventually feed onto a binary partner. This constant state of hyperrotation has a profound impact on the star's life story. By churning its internal plasma so vigorously, the rapid spin mixes fresh hydrogen from the outer layers down into the core, providing more fuel for nuclear fusion. This can make the star burn brighter and hotter than a similar, slow-spinning star, effectively extending its lifespan on the main sequence. Conversely, the powerful stellar winds driven by this spin can cause the star to lose mass at an accelerated rate, prematurely stripping it of the outer layers that would one day form a planetary nebula and shortening its visible lifespan. The star is caught in a tug of war between internal and external forces, its ultimate fate dictated by the gravitational dance that first set it spinning. While the gravitational chaos and rapid spins of these stars create spectacular magnetic storms, they also generate something far more energetic and invisible to our eyes: intense, high-energy X-ray radiation. For a typical solitary star like our Sun, X-ray emission is a quiet background hum, a byproduct of its hot corona. But point an X-ray telescope like Chandra or XMM Newton toward a septuple system, and the signal can be overwhelming. These stellar families are often brilliant beacons in the X-ray sky, shining with an intensity that betrays the incredibly violent processes unfolding within them. This unusual X-ray brightness points to two primary cosmic engines, both fueled by the system's extreme environment. The first is the sheer magnetic fury of the stars themselves. As we've seen, tidal forces can spin stars up to incredible velocities, and this rapid rotation supercharges their internal dynamos. The result is a corona, the star's multimillion-degree outer atmosphere, that is riddled with tangled magnetic field lines. These fields can snap and reconnect in colossal explosions, accelerating particles to near light speed and heating vast regions of plasma to temperatures so extreme that they glow not in visible light, but in high-energy X-rays. In a septuple system, you don't have just one of these hyperactive stars. You potentially have several, their combined X-ray output creating a persistent, high-energy fog that envelops the entire celestial family. The second, and often more powerful, source of X-rays originates not from the surfaces of normal stars, but from the space immediately surrounding a stellar corpse. In the crowded gravitational dance of a septuple system, material is constantly on the move. If one of the 7 stars is a white dwarf or a neutron star, the dense remnants of a dead star, its immense gravity can act as a cosmic vacuum cleaner. It can pull streams of gas directly from the atmosphere of a close binary companion or siphon material from the system's primordial debris disks. This stolen material doesn't fall directly onto the compact object. Instead, it forms a swirling, superheated structure known as an accretion disk. As gas spirals inward at a significant fraction of the speed of light, it is compressed and heated through friction to temperatures reaching millions of degrees. This process converts an enormous amount of gravitational energy directly into thermal energy, causing the entire disk to blaze with X-rays. The innermost rim of this disk, just before the material plunges onto the surface of the white dwarf or neutron star, is the hottest and brightest part of this cosmic powerhouse. In the case of a neutron star, the impact of the material on its solid surface can create even more localized, searingly hot spots that pulse with X-rays with every rotation of the star. For astronomers, these X-ray emissions are not just a spectacle, they are a critical diagnostic tool. By analyzing the spectrum of this X-ray light, its intensity at different energies, scientists can determine the temperature and density of the plasma in the accretion disk or the flaring corona. They can even identify the chemical elements present by the unique fingerprints or emission lines they leave in the high-energy light. Furthermore, if the compact object is a pulsar, a rapidly spinning neutron star, the X-rays may arrive in perfectly timed pulses, allowing for incredibly precise measurements of its rotation and any changes over time. This data provides a direct window into the physics of matter under the most extreme conditions imaginable, conditions that simply cannot be replicated in any laboratory on Earth. The X-ray glow of a septuple system is a direct broadcast of the complex and energetic interactions between its members, a high-energy signature of the relentless gravitational dynamics that define these extraordinary stellar families. Now, let's shift our focus from the high-energy violence of X-rays to a more subtle, yet equally profound gravitational phenomenon, the delicate choreography of tidal locking and resonance. In the intricate dance of a septuple system, stars don't just influence each other's paths, they can directly control each other's spin, creating relationships of profound intimacy and synchronicity. The primary mechanism for this is tidal locking, a process we're familiar with right here in our own solar system. Our moon is tidally locked to Earth, which is why we only ever see one side of it from our planet. It rotates on its axis at the exact same rate it orbits Earth, a perfect one-to-one sync. Apply this concept to stars and the implications are staggering. In a close binary pair within a septuple system, the immense gravitational pull each star exerts on the other can, over millions of years, slow their rotations until they achieve this same state of synchronous rotation. Imagine two stars so close that they are forever locked in an embrace, each one presenting the same face to its partner for all eternity. The side perpetually facing its companion would be relentlessly heated and bathed in intense radiation and stellar wind, while the far side would exist in a state of permanent night, potentially cooling significantly. This creates a star with a permanent hot pole and a cold pole, a drastic departure from the uniform sphere we typically imagine. But the gravitational symphony in these systems often plays more complex tunes than a simple duet. This is where the concept of orbital resonance comes into play, and it is one of the most elegant and mathematically beautiful phenomena in all of astronomy. A resonance occurs when the orbital periods of different pairs within the system settle into a ratio of small whole numbers. For instance, for every 3 orbits completed by one inner binary pair, an outer pair might complete exactly 2 orbits. This is known as a 3-to-2 resonance. Other common resonances are 2-to-1 or 3-to-1. These aren't coincidences, they are a natural outcome of gravitational systems evolving over immense periods of time, eventually settling into the most stable, energy-efficient configurations possible. These resonances act as a celestial stabilizing mechanism. The periodic gravitational tugs between the resonating pairs become predictable and reinforcing rather than disruptive. It's like pushing a child on a swing at the exact right moment in its arc. You add energy smoothly and maintain the rhythm. In a septuple system, these resonances can be the hidden glue that prevents the entire chaotic arrangement from flying apart, creating pockets of long-term stability within the gravitational storm. However, resonance is a double-edged sword. While it can create stability, it can also be a source of profound chaos if the system is perturbed. A resonance can amplify even the smallest gravitational nudge. If a passing star from outside the system or the sudden ejection of a member internally changes the mass distribution ever so slightly, it can knock a resonant pair out of their perfect sync. Once that precise gravitational rhythm is broken, the same forces that once provided stability can now begin to work against the system, pumping energy into orbits and making them more and more elliptical. This can lead to a cascade of destabilization, dramatically altering orbits and potentially leading to close encounters, collisions, or ejections over million-year timescales. The difference between a stabilizing resonance and a chaotic one can be a knife's edge, a testament to the delicate balance that governs these magnificent seven-sun families. The notion that planets could ever form amidst the gravitational turbulence of seven young stars seems to defy all logic. The sheer gravitational pull from so many massive bodies should, in theory, tear apart any nascent disk of gas and dust long before it could ever coalesce into a planet. Yet, against these astronomical odds, we have found them, resilient protoplanetary disks clinging to existence in the chaotic nurseries of young septuple systems. Their survival is one of the most astonishing discoveries in this field, a testament to nature's ability to find stability within the storm. These are not the serene, pancake-flat disks we see around single stars. The disks in septuple systems are survivors, and they bear the scars of their violent environment. They are often much smaller than their solitary counterparts, having been dramatically truncated by close gravitational encounters with their stellar siblings. Imagine a star's gravitational influence as a cosmic carving tool. A close pass can shear off the disk's outer edges, stripping away material and leaving behind a compact, dense disk that orbits much closer to its host star for protection. Furthermore, these disks are rarely flat. The competing gravitational tugs from the other six stars warp them into magnificent, complex shapes, twisted spirals, tilted rings, and wobbly distributions of material that look more like abstract sculptures than orderly construction sites. Despite this violence, their very existence proves that planet formation is not an impossibility here. It just follows a radically different set of rules. The process likely happens at a breakneck pace. In a comma system, planets have millions of years of relative peace to gently coalesce from colliding dust grains. In a septuple system, the window of opportunity is drastically shorter. The disk must form planets quickly before a stellar encounter rips it apart or scatters its precious building blocks into the void. This suggests that the mechanisms for planet formation might be supercharged in these environments, with gravitational instabilities in the dense, truncated disk causing material to collapse directly into planet-sized objects in a relatively short period of time. Any world that did manage to form in such a place would experience a reality we can scarcely imagine. Its orbit would be a complex, evolving path dictated by the combined gravity of seven suns. It might trace a stable path around one single star while being gently influenced by the more distant binary pairs, a configuration known as an S-type orbit. Or, in a truly breathtaking arrangement, it could be on a grand tour, orbiting the entire central binary pair of the system in a wide circumbinary path. The view from its surface would be a perpetual celestial festival. Multiple suns of different colors and intensities would dance across the sky in a complex, ever-changing clockwork. There would be periods of multiple sunrises and sunsets, times of perpetual daylight, and perhaps even moments where one star eclipses another, casting dramatic, shifting shadows across the landscape. The concept of seasons on such a world would be redefined beyond recognition. As the planet moves along its complex orbit and the other stars shift in their own intricate patterns, the amount of stellar energy it receives would fluctuate wildly and unpredictably. A season might last for a few weeks or for centuries, with temperatures swinging from scorching heat to deep freeze based on the current arrangement of its seven suns. The persistent gravitational stretching from these massive bodies would also likely make the planet itself incredibly volcanic, with a molten interior constantly churned by tidal forces. This is not a gentle, life-bearing world like Earth. It is a monument to cosmic persistence, a testament to the fact that even in the most extreme environments, the universe will still try to build new worlds. But perhaps the most breathtaking consequence of this stellar diversity is the sheer visual spectacle it would present to any observer. Imagine a sky not with one sun but filled with 7, each a different size, brightness, and hue. A brilliant, searing white or blue O-type star could dominate the view, its intense light bleaching the colors from everything around it. Nearby, a cooler, orange K-type giant might glow like a warm ember, while a faint, deep red M-type dwarf pulses slowly in the distance. This wouldn't be a uniform wash of light. It would be a dynamic, ever-changing painting of contrasting colors, with the stars constantly shifting positions in their complex gravitational dance. The shadows cast would be multicolored, and the concept of daylight would be entirely redefined by which combination of stars was above the horizon. This vibrant cosmic palette is a direct, visible manifestation of the complex and varied lives of the stars within, a daily reminder of the incredible astrophysical processes that built such a spectacular family. These minuscule wobbles, these astrometric shifts, are the whispers of the system's hidden architecture. Every star in a septuple system is perpetually tugged and pulled by the gravity of its siblings, causing it to trace a tiny, elliptical path around the system's common center of mass instead of moving in a perfectly straight line through space. For centuries, detecting this motion was beyond our technological grasp, as the shifts are often smaller than the apparent size of a coin viewed from thousands of miles away. But with the advent of space-based observatories like Gaia, which can measure the positions of stars with micrometer-level precision, we can now listen to those whispers and translate them into a detailed map of gravitational influence. In a simple binary system, this wobble is a clean, predictable ellipse, easily decoded to reveal the mass and orbital distance of the unseen companion. But place that same star within a web of 6 other gravitational partners, and its path becomes an incredibly complex spirograph pattern. Its motion is no longer dictated by one pull, but by 6 separate and constantly changing tugs. The star's astrometric wobble becomes a superposition of all these influences, a tangled signal where the gentle nudge from a distant brown dwarf is mixed with the violent yank from a close binary partner and the steady pull of the system's overall center of gravity. Isolating a single signal from this noise is one of the greatest computational challenges in modern astronomy. The process of untangling this web is a forensic exercise in gravitational deduction. Astronomers use complex algorithms to model the system, essentially creating a digital simulation with virtual stars of different masses on different orbits. They then run the simulation, tweaking the parameters, the mass of this star, the eccentricity of that orbit over and over again, until the predicted wobbles of the virtual stars perfectly match the precise astrometric data collected by the telescope. It's a painstaking process of elimination that can take years, but the rewards are profound. This technique has already been used to uncover previously hidden members of known septuple systems, objects too dim or too close to their brilliant partners to be seen directly. These discoveries often come in the form of low-mass red dwarf stars, the most common star type in the galaxy, but they can also reveal even more exotic inhabitants. The subtle, persistent tug of a super-Jupiter or a brown dwarf will imprint itself on the wobble of its host star, leaving a distinct signature that, once isolated, confirms the existence of a substellar object. In this way, astrometry doesn't just find hidden stars, it completes the planetary census of these extreme systems, revealing gas giants that formed in the cosmic chaos and managed to hold onto their stable orbits. Each decoded wobble is a testament to the hidden complexity of these stellar families, proving that even when we can't see a member of the system, its gravity still speaks volumes. After witnessing the chaotic gravitational dances and violent stellar encounters, it feels almost counterintuitive to discover that some of these magnificent seven-star families have achieved something remarkable: profound long-term stability. While systems like Nu Scorpii are cosmic demolition derbies, others have found an elegant gravitational balance persisting for billions of years, a time span that often exceeds the current age of our own solar system. This isn't a matter of luck, it's a direct result of their architectural genius, a specific orbital configuration that allows them to defy the inherent chaos of multi-body gravity. The secret to their longevity lies in a concept known as hierarchical stability. Imagine a set of perfectly crafted Russian nesting dolls. The smallest doll sits securely inside a slightly larger one, which itself fits inside another, and so on. This is precisely how a stable septuple system organizes itself gravitationally. At the very core, you find the tightest bond, a binary pair whirling around each other in a frantic, close orbit. This duo in its entirety is then treated as a single gravitational object. It acts as one half of a new, wider binary partnership with another pair of stars. That new, larger quartet then becomes a single unit orbiting with a third pair, and finally, the seventh star, or perhaps another binary, orbits this entire central cluster at a vast distance. This nested design is a masterclass in minimizing gravitational chaos. The key is the immense difference in orbital scales. The stars within the innermost binary are so close together that their gravitational bond is incredibly strong, acting as a single, consolidated mass for the rest of the system. The distances between these different hierarchical levels are so vast that the gravitational perturbations, those disruptive tugs that can lead to instability, are dramatically reduced. Close encounters, the primary drivers of stellar ejections and chaotic orbits, become exceedingly rare because each pair or group is effectively isolated within its own gravitational sphere of influence. This makes these ancient, stable systems far more than just celestial curiosities. They are unparalleled natural laboratories. For astrophysicists, they provide a perfect testing ground for theories of long-term gravitational dynamics. Our computer simulations of complex systems can only project so far into the future before tiny rounding errors accumulate and make the predictions unreliable. But these real-world septuple systems show us the actual outcome of billions of years of gravitational evolution. By studying their precise orbital parameters, we can reverse engineer the physics, refining our models and gaining deep insight into the fundamental rules that govern all gravitational systems, from star clusters to entire galaxies. Their enduring existence also provides crucial clues about the conditions of their birth. A system cannot simply decide to become hierarchical later in life. This structure must have been imprinted upon it during its formation. The fact that we see these stable hierarchies in systems that are billions of years old strongly suggests they were born this way, forming directly from a collapsing cloud of gas and dust that fragmented in this specific nested manner. They are living fossils, preserving the blueprint of their own creation and offering us a direct window into the processes that can build such breathtakingly complex and enduring celestial architectures. Yet for all the visual drama of these systems, some of their most crucial secrets are locked away in a dimension we cannot see, the subtle shifts in the very color of their light. This is the domain of Doppler spectroscopy, a technique so powerful it allows us to measure the frantic orbital dance of stars with breathtaking precision, simply by watching their light waves stretch and compress. In a septuple system, this doesn't just create a simple back and forth shift. It generates a chaotic symphony of spectral lines, a tangled signal that represents one of the most complex puzzles in all of observational astronomy. The principle itself is elegant in its simplicity. As a star moves toward us in its orbit, its light waves are compressed, shifting them slightly toward the blue end of the spectrum. As it moves away, the waves are stretched, shifting them toward the red. By meticulously measuring these shifts over time, astronomers can plot a star's radial velocity, its speed directly toward or away from us. In a binary system, this creates a clean, predictable sine wave-like pattern. But introduce 6 other gravitational partners, and that clean sine wave dissolves into a frenetic, jagged line. The star is no longer being tugged by one source, it's being simultaneously pulled by 6 others, each with their own orbital period and strength. Its radial velocity becomes a superposition of all these influences, a complex signal where the gentle pull of a distant companion is buried under the violent yank of a close binary partner. Decoding this knotted signal is a task far beyond human calculation. It requires the raw power of modern supercomputers. Astronomers feed all the observed radial velocity data into sophisticated modeling software, which then runs millions of simulations. It tests every conceivable combination of stellar masses, orbital distances, and orbital eccentricities, searching for the one unique model where the predicted velocity curves for all 7 stars perfectly match the maddeningly complex data collected by the telescopes. This computational brute force is the only way to reverse engineer the system's architecture, transforming an incomprehensible jumble of data points into a precise quantitative map of masses and orbits. The payoff for this immense effort is a treasure trove of fundamental data. By successfully untangling the spectral lines, we can weigh each star with incredible accuracy, determining its mass, the single most important property governing its life and death. We can also chart the precise shape of every orbit, learning which are nearly circular and which are wildly elliptical. But sometimes the models reveal something even more profound, a tiny, persistent anomaly that the basic gravitational model cannot explain. The entire velocity curve might appear to slowly rotate over time, a phenomenon known as relativistic precession. This is a direct signature of Einstein's general theory of relativity at work. The immense gravity of the stars is causing their orbits themselves to precess or wobble like a slowly spinning top. Detecting this effect in a multi-star system is a stunning confirmation that even on these vast scales, the universe obeys Einstein's rules. Perhaps the most thrilling anomaly of all is a minuscule, repeating wobble superimposed on the already complex stellar dance. After accounting for the gravitational pull of all 6 stellar siblings, a single star might still show a tiny, periodic shift in its velocity. This is the telltale signature of an exoplanet. Its gentle gravitational tug, though dwarfed by those of the stars, is just enough to make its host star wobble slightly in place. Finding a planet in this way within a septuple system is a breathtaking feat of detection. It means that despite the gravitational chaos, the cosmic imperative to build planets persists, and we now have the tools to find them even in the most extreme environments imaginable. While the intricate dances and violent encounters within septuple systems are captivating in their own right, their true cosmic significance extends far beyond their immediate stellar family. These rare and dynamic structures, though few in number, may act as powerful engines of change on a galactic scale, shaping the evolution of the entire Milky Way and beyond. Their unique ability to catapult stars into the void and seed space with the building blocks of planets and life gives them an influence that is vastly disproportionate to their rarity. The most direct way these systems leave their mark on the galaxy is through the production of runaway stars. As we've seen, the gravitational slingshot effect within a crowded septuple system can eject a massive star at incredible speeds. This doesn't just alter the system itself, it launches a brilliant, massive projectile across hundreds or even thousands of light years. These runaway stars become cosmic pioneers, carrying their intense ultraviolet radiation and powerful stellar winds into the pristine, quiet regions of the galaxy. They can tear through nearby molecular clouds, their radiation compressing the gas and potentially triggering a new wave of star formation in their wake. In this way, a single chaotic event in a distant septuple system can initiate a chain reaction of stellar birth far from its point of origin, effectively spreading the seeds of new solar systems across the galactic disk. Furthermore, the violent deaths of these massive stars are fundamental to the chemical richness of the universe. The very atoms that make up our world, the iron in our blood and the calcium in our bones, were forged in the cores of stars and scattered across space in supernova explosions. Septuple systems, with their propensity for housing massive, fast-living stars, are prolific factories for these heavy elements. When one of these giants goes supernova, the explosion floods its local region with a newly synthesized cocktail of elements, enriching the surrounding interstellar medium. This enriched gas then cools and condenses, eventually forming new generations of stars and planets. Each new stellar family born from this material starts its life with a richer chemical endowment than the last, allowing for the formation of rocky planets and the complex chemistry that underpins life. The presence of a septuple system in a region of space acts as a powerful catalyst for this process, repeatedly seeding its neighborhood with the essential elements for building worlds. Understanding the life cycles of these systems is therefore like reading a history book of our galaxy's chemical evolution. By studying the ages and compositions of the stars within a septuple system, astronomers can trace back the timeline of star formation in that particular region. A system with stars of varying ages might tell a story of multiple episodes of star birth, perhaps triggered by the shockwave of a nearby supernova itself. The specific ratios of heavy elements found in their atmospheres serve as a fossil record, revealing the composition of the original molecular cloud from which they formed and the particular brand of nucleosynthesis that occurred within their most massive siblings. In piecing together the history of these extreme systems, we are ultimately piecing together our own cosmic ancestry, tracing the lineage of the elements that make up our solar system and ourselves back to their dramatic origins in these magnificent and chaotic stellar families. Even the most stable cosmic arrangements are not immune to dramatic change, a fact highlighted by one of the most perplexing discoveries in the study of these systems, the case of the missing stars. There are a handful of septuple systems where meticulous historical records, some dating back over a century, tell a contradictory story to what our modern telescopes now reveal. Early observational logs and photographic plates clearly indicate the presence of a seventh member, a star that shone with a specific brightness and color. Yet, when we train our most advanced instruments on that same patch of sky today, that star is simply gone. It has vanished without a trace, leaving behind only its gravitational ghost and a profound cosmic mystery. The most straightforward explanation for this disappearance is a stellar ejection that we simply missed. As we've seen, the gravitational slingshot effect can violently expel a star from the system at tremendous speed. If such an event occurred centuries or millennia ago, the star would have long since departed, traveling so far from its original home that the connection is no longer obvious. We would be left looking at the remaining 6 stars, their orbits subtly reconfigured from the loss of their sibling, with no other visible evidence of what transpired. The missing star would now be a lone rogue drifting through the interstellar void, its origin story lost to time. A far more exotic and theoretically fascinating possibility is that the star never left at all. Instead, it might have undergone a direct collapse into a black hole. Our standard model of stellar death involves a spectacular supernova explosion, a brilliant flash that would be unmistakable in historical records. However, some theories suggest that the most massive stars might sometimes skip this explosive finale. If a star is sufficiently massive and collapses rapidly enough under its own immense gravity, it might simply implode, its light winking out as an event horizon forms around it, swallowing the star whole without so much as a cosmic whimper. This direct collapse would leave behind a stellar mass black hole, an invisible gravitational anchor, as the only testament to the star's former existence. The sudden absence of its light would be the only sign that a catastrophic transformation had occurred. A third, more subtle option involves not the destruction of the star, but its concealment. The star might still be there, but something has come between us and it. Septuple systems, particularly young ones, can be surrounded by vast, dynamic clouds of gas and dust, the leftover material from their formation. A dense, previously unseen knot of this debris could have drifted directly into our line of sight, effectively placing a cosmic curtain in front of the star. From our perspective, the star would appear to dim dramatically or vanish completely, its light absorbed or scattered by the intervening dust. This wouldn't be a permanent disappearance, but rather a temporary occultation that could last for decades or even centuries before the cloud moves on. Each of these explanations carries its own set of implications and challenges our understanding. A past ejection forces us to reconsider the long-term stability of even the most hierarchical systems, suggesting that periods of calm can be punctuated by sudden, violent events. A direct collapse would revolutionize our models of stellar death, proving that the universe has a quieter, more efficient way of creating black holes than the supernova we thought were mandatory. And an obscuration by dust reminds us that our view of the cosmos is always partial and filtered, subject to change based on the ever-shifting architecture of the interstellar medium. The mystery of the missing stars is a powerful, humbling reminder that these magnificent systems are not static exhibits in a museum. They are dynamic, evolving entities, capable of changes so profound they can erase a sun from the sky and leave us to piece together the clues of its fate. While the brilliant light of 7 stars dominates the visible spectrum, some of the most telling secrets of these systems are revealed in the invisible warmth of infrared light. Many septuple systems emit a significant and persistent excess of infrared radiation, a telltale glow that cannot be explained by the stars themselves. This energy signature points to the presence of something far more subtle yet profoundly revealing: vast clouds of warm dust. Unlike the cold, pristine dust of undisturbed nebulae, this dust is being actively heated, often to temperatures of hundreds of degrees, and its existence is a direct indicator of relentless, violent activity occurring within the gravitational arena. The most compelling source for this warm dust is a catastrophic collision. In the crowded confines of a septuple system, the delicate gravitational dance that might allow asteroids and planets to orbit peacefully in a single star system is constantly disrupted. The paths of smaller bodies are perpetually perturbed by the competing tugs of multiple suns, sending them on chaotic trajectories that drastically increase the odds of a high-speed impact. Asteroids shatter against each other, comets are flung into planetesimals, and even fully formed planets might experience apocalyptic collisions, all of which grind solid material into fine, hot dust. This dust then spreads out, absorbing the intense starlight and re-radiating it as the infrared excess we detect from light years away. But the scale of destruction isn't limited to small bodies. In the most extreme scenarios, the infrared excess could be the aftermath of a stellar collision. While incredibly rare, the chaotic orbits in a system like Nu Scorpii could, over billions of years, lead 2 stars to a fatal rendezvous. The resulting collision would be a titanic event, unleashing more energy than a supernova and utterly vaporizing both stars into a colossal, expanding cloud of incandescent gas and dust. This cloud would initially blaze with visible light before cooling and settling into a massive, enduring shell of warm material that would glow brightly in the infrared for millennia. The detection of such a signal would be the ghostly aftermath of a cosmic catastrophe of almost unimaginable proportions. For astronomers, this infrared glow is far more than just a curiosity. It's a powerful diagnostic tool. By analyzing the spectrum of this infrared light, breaking it down into its specific wavelength, scientists can determine the precise temperature of the dust, which reveals its distance from the central stars. They can also identify the composition of the dust itself, finding the mineralogical fingerprints of silicates, carbons, and other compounds. This allows them to distinguish between dust created from the collision of rocky, Earth-like planets versus that from icy comets or even the unique debris of a stellar merger. The persistent infrared excess acts as a continuous broadcast of the system's destructive history, a permanent record of the violence that shapes these extreme environments and a reminder that even in the vastness of space, traffic jams of cosmic proportions can have spectacularly messy consequences. So far, we've explored what we can learn from the light these systems emit and the gravitational wobbles we can measure. But there exists an entirely different way to study them, one that doesn't rely on light at all, by listening to the ripples they create in the very fabric of spacetime itself. The prospect of detecting gravitational waves from a septuple system represents the next frontier in understanding these cosmic families, offering a direct line into their most energetic and hidden processes. Our current generation of observatories like LIGO and Virgo are engineering marvels designed to catch the most colossal collisions in the universe. They are tuned to hear the final, milliseconds-long chirp of two black holes or neutron stars spiraling into each other in a cataclysmic merger. The waves from such an event are immense, powerful enough to stretch and compress the space between our mirrors by a tiny fraction of the width of a proton. The close binaries within a septuple system, however, produce a very different kind of signal. Instead of a final death cry, they generate a continuous, long-lasting hum, a persistent gravitational wave background that is, for now, just below our current threshold of detection. This hum is generated by any massive object that isn't perfectly symmetrical and is accelerating. In a close binary pair, the two stars are perpetually accelerating as they whip around their common center of gravity. This motion creates a constant, rhythmic emission of gravitational waves that steadily drains orbital energy from the system. For most binaries, this energy loss is so minuscule it takes billions of years to have any effect. But in the incredibly tight, fast-moving orbits found at the heart of some septuple systems, this process is supercharged. The waves they emit are stronger and could, with the right technology, be heard across the galaxy. Future observatories, like the proposed space-based mission LISA, are being designed specifically to tune into this lower-frequency gravitational symphony. While LIGO listens for the high-frequency crashes of symbols, LISA will be attuned to the deep, constant cello notes of ongoing cosmic motion. A close binary in a septuple system would be a prime target, its signal acting as a continuous beacon. By monitoring the subtle changes in the frequency and amplitude of this signal over years, scientists could measure the masses of the two stars with unparalleled accuracy, chart the precise shape and orientation of their orbit, and even detect the subtle effects of other stars in the system tugging on the binary pair, all without a single photon of light making the journey to our telescopes. This gravitational wave data would provide a completely independent and extraordinarily precise test of everything we think we know about these systems. It would act as a perfect cross-check for the models we've built from astrometric and spectroscopic data, potentially confirming our theories or revealing hidden flaws. Most excitingly, it could unveil the presence of entirely dark companions like a quiet black hole orbiting with the binary whose gravitational influence would imprint itself on the wave pattern. Listening to the space-time ripples from a septuple system wouldn't just be another way to observe it. It would be like developing a whole new sense, allowing us to perceive the true mass and motion of these celestial families in a way light alone could never allow. Even in the most stable of these 7 star families, the environment is far from tranquil. Lurking within the complex magnetic fields of these stars is a potential for sudden, catastrophic violence, the stellar flare. While our own sun produces flares that can disrupt satellites and power grids, the flares observed in septuple systems operate on an entirely different scale. These are not mere bursts of light. They are titanic eruptions of energy, often orders of magnitude more powerful than anything our solar system has ever witnessed, and their origins are deeply tied to the chaotic gravitational dance that defines these stellar families. The engine behind these apocalyptic events is a process known as magnetic reconnection. Imagine the magnetic field lines surrounding a star as vast, twisted rubber bands storing immense amounts of energy. In the turbulent environment of a septuple system, these fields can become incredibly complex and strained. Tidal forces from nearby stars constantly knead and distort the stellar surfaces, while the rapid rotation of tidally locked binaries wins the magnetic fields tighter and tighter. Eventually, the stress becomes too great. The field lines snap, breaking and reconnecting in a new, lower-energy configuration. In that instant of reconnection, all the pent-up magnetic energy is released in a cataclysmic explosion, accelerating charged particles to nearly the speed of light and heating vast volumes of plasma to tens of millions of degrees. What makes these flares so uniquely unpredictable in a septuple system is their potential trigger mechanism. While a solitary star might flare due to its own internal dynamics, here the eruption can be set off by an external gravitational nudge. A close pass between two stars, even if they don't physically touch, can send powerful tidal waves rippling through their interiors. This sudden disturbance can be the final straw that triggers the magnetic reconnection event, meaning a flare on one star could be directly caused by the orbital motion of a sibling millions of miles away. The timing of these eruptions is therefore tied to the chaotic orbital periods of the system, making them appear random and impossible to forecast with any long-term accuracy. The sheer power unleashed is almost incomprehensible. A single large flare from one of these stars can release more energy in a few minutes than our sun will emit across an entire century. This energy floods the system across the entire electromagnetic spectrum, from radio waves to lethal gamma rays. For any hypothetical planet orbiting within the system's habitable zone, this would not be a habitable environment at all. It would be a shooting gallery. The intense X-ray and ultraviolet radiation from a major flare would violently strip away a planet's atmosphere, boiling off oceans and sterilizing the surface. Repeated flare events would ensure that any emerging chemistry necessary for life would be repeatedly scoured clean, making these systems some of the most hostile real estate in the entire galaxy. Beyond the immediate radiation blast, the ejector from these flares presents a second, slower-moving threat. Coronal mass ejections, massive clouds of magnetized plasma hurled into space, would regularly billow out from the flaring star. A planet caught in the path of such a storm would have its own magnetic field, if it has one, severely compressed, allowing energetic particles to rain down on the surface. For a world already struggling to hold onto an atmosphere, these particle showers would act like a cosmic sandblaster, slowly eroding any chance for a stable climate to develop. The unpredictable nature of these flares means a planet could experience long periods of relative calm, only to be blindsided by a cataclysmic event that resets the clock on any potential biological evolution, forever maintaining these spectacular systems as breathtaking celestial wonders but profoundly desolate worlds. Yet even amidst the unpredictable violence of stellar flares, there exists a phenomenon of such precise and ordered beauty that it serves as the ultimate tool for cosmic measurement, the triple eclipse. Picture the delicate choreography required for this event. 3 individual stars, each on their own separate orbit within the vast clockwork of the septuple system, must align perfectly along our line of sight. For a brief, precious window, they all converge, with one star passing in front of another, which itself is transiting a third. The resulting drop in the system's combined light is not a simple dip. It's a complex, multi-tiered dimming event, a light curve with a story so detailed it allows astronomers to reverse engineer the system's architecture with jaw-dropping precision. The data encoded within this intricate light pattern is a veritable gold mine. A standard binary eclipse provides two crucial data points, the sizes of the stars and the tilt of their orbit. But a triple eclipse adds an entirely new dimension literally. It reveals the full three-dimensional layout of that specific stellar grouping, the precise timing of the secondary and tertiary dimmings, the specific depths of each dip in brightness, and the overall shape of the composite light curve together act as a cosmic CT scan. Astronomers can use this information to calculate not just the diameters of all three stars, but also their mutual distances, the exact inclinations of their orbital planes relative to each other, and even refine their mass estimates to an extraordinary degree of accuracy. It's the difference between seeing a shadow play on a wall and being able to walk around the puppets themselves to see how they're all connected. Capturing and decoding these events is a monumental task of patience and prediction. Because the orbits of all 7 stars are constantly interacting, the precise alignment needed for a triple eclipse is incredibly rare, sometimes occurring only once every few decades or even centuries. Astronomers must run sophisticated computer models of the entire system's gravitational dance for millions of years into the future, and pass to pinpoint the exact moments these celestial syzygies will occur. When a predicted window opens, telescopes around the world and in space are trained on the system, gathering a flood of photometric data across multiple wavelengths to capture every nuance of the dimming. The effort is well worth it, as the payoff fundamentally anchors our entire understanding of the system. The exquisitely precise stellar parameters pulled from a triple eclipse become fixed points in our models. The masses and sizes of those 3 stars are no longer estimates, they are known quantities. This then allows scientists to much more accurately calculate the masses of the other 4 stars in the system by observing how they gravitationally respond to these now well-defined anchors. A single, well-observed triple eclipse can transform our model of a distant septuple system from a plausible sketch into a precise and quantitative blueprint, confirming the existence of hierarchies, revealing the true scale of orbits, and ultimately gifting us with a deeper appreciation for the ordered beauty hidden within the apparent chaos. This journey through the gravitational dynamics and violent flares of these systems brings us to perhaps their most profound long-term mystery, their ultimate fate. The stars within a septuple system do not live and die in isolation. Their extraordinary proximity writes a shared evolutionary story far stranger than anything a solitary star could experience. This shared destiny creates what can only be described as a cosmic laboratory for exotic stellar metamorphosis, where the death of one star can directly dictate the rebirth of another, all within the same tightly bound family. One of the most dramatic transformations arises from the process of mass transfer within a close binary pair. Imagine a scenario where a more massive star evolves faster, swelling into a red giant. If it has a close companion, its outer layers can overflow their gravitational container and spill onto the smaller star. This isn't a gentle donation. It's a stellar theft that can completely strip the giant star down to its bare, helium-rich core long before it would have naturally shed those layers itself. The result is a bizarre object known as a helium star, a hot, exposed stellar core furiously burning helium, looking nothing like its original form. This prematurely revealed core then continues its life on an accelerated and altered path, its ultimate fate as a white dwarf or neutron star now arriving millions of years ahead of schedule. Meanwhile, the star on the receiving end of this material gets a new lease on life. This recipient star is suddenly inundated with a fresh supply of hydrogen fuel, which settles onto its surface and rejuvenates its core. To an outside observer, this star now appears brighter, hotter, and bluer than other stars of a similar age in the system. It has become a blue straggler, a star that seems to defiantly ignore the rules of stellar evolution, appearing paradoxically younger than its siblings. In a septuple system, the presence of a blue straggler is a permanent chemical monument to a past act of stellar cannibalism, a visible record of mass transfer that occurred eons ago. Over billions of years, this leads to the system's final act, the creation of a diverse stellar graveyard. Because the stars began with different masses and then experienced these wildly different evolutionary paths due to their interactions, they will die in a variety of ways. Some will end their lives relatively quietly, shedding their outer layers to leave behind a dense, Earth-sized ember known as a white dwarf. Others, born as more massive stars or having gained mass from a partner, will die in violent supernova explosions, their cores collapsing into ultra-dense neutron stars or perhaps even vanishing behind the event horizon of a black hole. The end result is a single gravitational family that could contain a mix of main sequence stars, a helium star, a white dwarf, a neutron star, and a black hole all orbiting one another. This final configuration becomes a playground for extreme physics. A white dwarf could orbit close enough to a regular star to begin siphoning material again, building up until it undergoes a thermonuclear explosion as a nova, or even collapses entirely in a Type Ia supernova. A neutron star or black hole could pull material from a companion, forming a brilliant accretion disk that glows with X-rays. The gravitational waves from these exotic pairs would be a strong, continuous signal. This means a single ancient septuple system is not just a collection of stars. It is a timeline of cosmic evolution and a museum of stellar corpses, each exhibit telling a different story of birth, interaction, and death, all held together by the relentless pull of gravity. Beyond the violent flares and precise eclipses, there exists a far more subtle way to understand these stars by listening to their unique internal music. This field of study is known as astroseismology, and it involves analyzing the incredibly tiny, rhythmic pulsations that naturally occur on the surfaces of stars. Think of it like this: just as geologists use the seismic waves from earthquakes to map the hidden interior of our planet, astronomers can use the light waves from these stellar vibrations to see deep inside a star. In the complex environment of a septuple system, this technique becomes an extraordinarily powerful tool for uncovering secrets that would otherwise remain forever hidden. These pulsations are not random flickering. They are standing waves, resonant frequencies that travel through the star's interior and cause its entire surface to gently rise and fall in a predictable pattern. The star essentially rings like a colossal bell. The specific frequencies of these oscillations are dictated by the conditions inside the star. Its density, temperature, and composition all alter the sound speed within, which in turn changes the pitch of the vibrations. By meticulously measuring these frequencies, scientists can perform a kind of cosmic ultrasound, constructing a detailed cross-section of the star's internal structure from its searingly hot core to its turbulent outer layers. For stars in a septuple system, this data is revolutionary. It allows astronomers to determine the age of individual stars with unprecedented accuracy. A star's internal rotation rate changes as it ages, and this affects its pulsation modes. By measuring these modes, we can effectively carbon date each star within the system, revealing if they were all born at the exact same time or if there were multiple, distinct episodes of star formation. This helps solve the pivotal question of whether all 7 members are true siblings from a single birth cloud, or if some were adopted through capture events later in life. Furthermore, astroseismology can reveal the astonishing impact of tidal forces on a star's very heart. The relentless gravitational tug of war in a close binary can literally spin up the star's core, making it rotate much faster than its outer layers. This differential rotation is incredibly difficult to detect by any other means, but it leaves a clear signature in the pulsation frequencies. By analyzing this, we can understand how the gravitational dance with 6 siblings has fundamentally altered a star's internal dynamics, affecting its magnetic field generation and ultimately its long-term evolution. This gives us a direct window into how the extreme environment of a septuple system doesn't just change a star's orbit, it changes the star itself from the inside out. This recurring theme of revision in astronomy highlights a humbling truth. Some of the most fascinating cosmic discoveries aren't about finding something entirely new, but about finally seeing what was always there. Several star systems, long catalogued and studied as sextuples or quintuples, have recently been upgraded to full septuple status, not because the stars themselves changed, but because our technology and techniques finally caught up to their complexity. These reclassifications are more than just a paperwork update. They are a fundamental shift in our understanding of these stellar families and a stark reminder of the limits of our perception. The primary reason for these decades-long misidentifications boils down to 2 major observational challenges: faintness and proximity. A dim red dwarf star, for instance, possesses a fraction of the mass and brightness of its brilliant O-type or B-type siblings. In the glare of those dominant stars, its faint light is utterly washed out, making it as invisible as a firefly next to a spotlight. For centuries, that 7th member simply wasn't bright enough for our telescopes to detect against the overwhelming backdrop. The other great hiding technique is orbital intimacy. A pair of stars locked in an incredibly tight orbit can appear as a single, slightly blurry point of light, even to the most powerful optical telescopes. We might detect a slight anomaly in its spectrum or a subtle wobble in its motion, but resolving it definitively as 2 distinct stars requires an entirely different level of precision. The tools enabling these upgrades are nothing short of revolutionary. Space-based observatories like Gaia have provided astrometry, the precise measurement of stellar positions, with micro-arcsecond accuracy. This allows astronomers to detect the telltale wobble in a star's path caused by the gravitational tug of an unseen companion, even if that companion is too dim to see directly. Meanwhile, advanced adaptive optics on ground-based telescopes and techniques like optical interferometry have dramatically sharpened our vision, effectively cancelling out the blurring effects of Earth's atmosphere. This has finally allowed us to split apart those previously merged points of light, revealing 2 stars where we once only saw one. Each technological leap doesn't just give us a better picture, it rewrites the textbook. This ongoing process of reclassification forces us to confront an exciting and daunting possibility. Our current census of multiple star systems is undoubtedly incomplete. For every system we've successfully upgraded from sextuple to septuple, there are likely many more that are currently mislabeled. The septuples we know about might secretly be octuples or nonuples, their full membership still hidden from our view. This means the already rare population of these extreme systems is probably larger than we think, suggesting that the hierarchical gravitational architectures needed to bind so many stars together might be a more common outcome of star formation than our current maps indicate. Every one of these upgrades sends ripples through our models of stellar and galactic evolution. Adding a 7th star, even a faint one, changes the total mass of the system, which in turn affects how we model its long-term stability and the gravitational interactions between all members. It can explain previously perplexing orbital anomalies or chemical peculiarities that didn't make sense with only 6 stars in the equation. With each discovery, we are not just adding a dot to a map, we are adding a crucial variable to a billion-year gravitational equation, slowly refining our understanding of how complex systems behave across the lifetime of the galaxy. This continuous process of revision isn't a sign of failure in astronomy. It is the very heartbeat of the scientific method, a testament to our relentless pursuit of a clearer, more complete picture of the universe. Amid the breathtaking complexity of 7 stars dancing together, there exists a profound and unexpected utility. one that reaches far beyond the system itself to help us measure the entire cosmos. This utility hinges on a cosmic gift found in some of these systems, the eclipsing binary. When such a pair exists within a septuple family, it transforms from a fascinating object of study into one of the most precise calibration tools in all of astronomy, a fundamental rung on what scientists call the cosmic distance ladder. The core principle behind this is deceptively simple, rooted in a basic property of light. An object's apparent brightness in our sky depends on both its true, intrinsic power and its distance from us. An incredibly brilliant star very far away can appear just as dim as a feeble star relatively close by. This creates a fundamental problem in astronomy. How can we know if a star is truly dim or just very distant? The solution is to find stars whose intrinsic brightness we can know for certain, independent of their distance. These are called standard candles, and an eclipsing binary in a septuple system is one of the most reliable examples we have. Here's how it works. As we've seen, the eclipses themselves are a goldmine of data. The precise timing and depth of the dips in the light curve allow astronomers to calculate the physical sizes of the two stars with extraordinary accuracy. Combined with spectroscopic measurements that reveal their orbital speeds, we can then use Newton's laws of motion to calculate their masses. These two properties, size and mass, are the master keys. They allow astrophysicists to plug the numbers into well-established models of stellar structure and evolution, which then spit out the star's true intrinsic brightness or absolute magnitude with very little uncertainty. We essentially reverse engineer the stars to discover exactly how much light they should be emitting. Once we know that number, measuring distance becomes a straightforward calculation. We simply compare that known intrinsic brightness to how dim the star actually appears from our vantage point here on Earth. The amount of dimming is directly related to the square of the distance. We can precisely calculate just how far away the system must be to make that brilliantly powerful star look as faint as it does in our telescopes. This provides a direct geometric distance measurement to the septuple system itself, independent of any other chain of assumptions. But the importance of this measurement doesn't stop at the system's edge. These meticulously calibrated septuple systems become anchor points for the entire cosmic distance ladder. This ladder is a series of methods, each building upon the last, that allows us to measure distances across the universe. The first rung consists of ultra-precise measurements within our solar system. The next rung relies on nearby stars, like those in septuple systems with eclipsing binaries, to gauge distances within our own galaxy. This is crucial because it allows us to calibrate the next type of standard candle, which are pulsating stars called Cepheid variables. Cepheids have a special property. Their pulsation period is directly tied to their intrinsic brightness. But to know exactly what that relationship is, we first need to measure the distance to a few Cepheids directly to calibrate the scale. And how do we measure those distances accurately? Often by finding Cepheids that reside in the same galaxy as a well-calibrated septuple system. By having that independent, precise distance from the eclipsing binary, we can perfect our understanding of the Cepheid period luminosity relation. We can then use those now perfectly calibrated Cepheids to measure distances to far more distant galaxies. This chain of measurement ultimately leads us to the most distant supernova, which are used to probe the expansion rate of the entire universe. A tiny error in the first rung of the ladder, the distance to a local star, becomes a massive error billions of light years away. Therefore, the more precise we can be with our closest standard candles, the more reliable our entire view of the universe's scale and history becomes. A single, complex family of 7 stars with its intricate eclipses therefore provides a fundamental anchor for cosmology itself, helping to refine our measurement of the Hubble constant and understand the fate of everything we see. Imagine for a moment that you're standing on the surface of a world nestled within a septuple star system. Your sky is not dominated by a single sun, but is instead a constantly shifting masterpiece of light and motion. Directly overhead, a pair of brilliant blue stars might be locked in a tight, rapid dance, completing an orbit in mere days. Off to one side, a cooler, orange giant hangs like a warm ember, while in the opposite direction, a faint red dwarf pulses slowly. The concept of a simple sunrise or sunset becomes utterly meaningless here. Instead, your day is governed by an unpredictable celestial clockwork where periods of blinding multi-sun daylight gradually give way to a twilight illuminated by a shifting combination of distant, colored suns and perhaps only brief, profound darkness when all 7 stars are briefly below the horizon. The very rhythm of life on such a world would be dictated by this chaotic light cycle. Photosynthetic organisms, if they could evolve, would face an incredible challenge. They might develop leaves capable of rapidly adjusting to wildly different light intensities and spectra, or perhaps lie dormant for long periods before exploding into growth during a rare extended stretch of optimal sunlight from a particular stellar combination. The idea of seasons as we know them would be completely rewritten. A summer might occur when a specific configuration of stars aligns to provide maximum heating, lasting for decades, only to be followed by a sudden, stellar winter, if that configuration is disrupted by the gravitational dance, plunging the world into a deep freeze. This profound speculation isn't just science fiction, it's a direct extension of the orbital mechanics we observe. The potential for such a world, often called a Tatooine-like planet but on a scale far beyond 2 suns, forces us to radically expand our definition of a habitable zone. We can no longer think of it as a simple, static shell around a single star. In a septuple system, the habitable zone becomes a dynamic, warped volume of space, with its boundaries pulsating inward and outward as stars move closer and further apart in their orbits. A planet might spend part of its long year within this life-friendly region, only to be flung outside it for another period, creating a stop-start potential for biological evolution that is utterly alien to our own experience. While the chances of finding life as we know it in such a gravitationally stressful and radiation-bathed environment seem incredibly slim, these systems spark a crucial philosophical shift in our search for life beyond Earth. They challenge our Earth-centric assumptions and force us to consider truly alien biologies. Could life arise not on a tranquil planet like our own, but on a world where resilience is defined by withstanding extreme and fluctuating conditions? Might organisms harness the intense magnetic fields or tidal energy for metabolism, rather than relying on sunlight alone? By pushing our imagination to these limits, septuple systems don't just show us where to look for life, they fundamentally redefine what we might be looking for, reminding us that the universe's creativity undoubtedly far exceeds our own. As we chart the complex gravitational dances within these 7 star families, our most sophisticated computer models begin to unveil a startling truth. For some of these systems, their beautiful chaos is not a permanent state, but a prelude to an ultimate, spectacular demise. Orbital simulations, which plot the paths of these stars millions of years into the future, predict that certain configurations are on an inescapable collision course. The same gravitational tides that currently spin stars up and warp their disks are, in these cases, slowly but relentlessly sapping orbital energy, causing their paths to decay over cosmic timescales. What we are witnessing is not a stable equilibrium, but a slow-motion countdown to a celestial catastrophe of almost unimaginable scale. The potential outcomes of such a stellar collision depend entirely on the participants involved. One of the most breathtaking possibilities is the merger of 2 massive main sequence stars. Picture 2 titans, each many times the mass of our Sun, their outer atmospheres already brushing against each other in a final, dizzying spiral. As their cores finally converge, the resulting object would be a behemoth, a hypergiant star so colossal and luminous it would briefly outshine entire galaxies. This newborn Leviathan would be a profoundly unstable object, burning through its nuclear fuel at a prodigious rate and shedding its outer layers in powerful, glowing winds that would enrich the surrounding system with newly forged heavy elements. Its life would be spectacular but tragically short. A far more violent finale awaits if one of the colliding bodies is already a stellar remnant. Imagine a scenario where a white dwarf, the Earth-sized cinder of a dead star, is nudged onto a path that sends it spiraling into the core of a living, red giant companion. The white dwarf, composed of ultra-dense degenerate matter, would plow through the giant's diffuse outer layers without slowing, eventually reaching its helium-rich core. The sudden injection of dense material and the immense shock waves would likely trigger a runaway thermonuclear explosion, a Type Ia supernova. This titanic detonation would momentarily outshine all 7 of the system's stars combined, and could potentially vaporize any nearby planets and severely disrupt the orbits of the remaining stellar siblings, fundamentally altering the gravitational architecture in an instant. Perhaps the most enigmatic result of a future collision would be the formation of an intermediate mass black hole. This could occur through the direct merger of 2 already dense stellar remnants, like neutron stars, or through the collapse of a hypergiant star formed from a prior merger. Ranging from 100 to 100,000 solar masses, these objects occupy a crucial gap between the stellar mass black holes formed from collapsing stars and the supermassive monsters that lurk in galactic centers. The presence of such an object within a septuple system would instantly transform it into a dominant gravitational anchor, its powerful pull dictating the motions of the surviving stars and potentially acting as a catalyst for further mergers and accretion events. While these events are millions of years in the future, their inevitability forces a profound shift in how we view these systems. They are not static exhibits in a cosmic museum. They are dynamic time bombs, their fates sealed by the initial conditions of their birth and the unyielding laws of gravity. Each close encounter, each transfer of mass, and each subtle orbital decay is another tick of the clock, moving them incrementally closer to a finale that will be both an end and a spectacular new beginning. From the gravitational chaos of stellar slingshots to the profound silence of dark companions, the journey through these 30 discoveries reveals a universe far more inventive and dynamic than we ever imagined. Septuple star systems are not merely astronomical curiosities. They are cosmic crucibles where the fundamental laws of physics are stretched, tested, and sometimes rewritten. They challenge the very definition of a solar system, proving that planets can form against unimaginable odds and that stellar relationships can range from harmonious hierarchical order to spectacular, unpredictable chaos. Each system tells its own unique story, a narrative of birth, interaction, and evolution written in light, gravity, and elemental chemistry. The study of these magnificent families is a testament to human curiosity and technological ingenuity. It is a field propelled by the painstaking analysis of starlight, the meticulous decoding of wobbling orbits, and the patient observation of eclipses that occur once in a century. Every new telescope, every advanced algorithm, and every space-based observatory peels back another layer of mystery, transforming what was once a single point of light into a detailed map of gravitational influence and stellar diversity. The upgrades from sextuple to septuple systems are a powerful reminder that our current understanding is merely a snapshot, a work in progress that is constantly being refined with each passing year. As we look to the future, the potential for discovery only grows more exciting. Next-generation telescopes, both on the ground and in space, will peer into the dusty nurseries of young systems with unprecedented clarity. Gravitational wave observatories will begin to tune into the low-frequency hum of these celestial choirs, allowing us to hear the universe in a completely new way. We will undoubtedly find more septuple systems, and within them, even stranger phenomena, perhaps planets with 7 suns, more hidden black holes, or evidence of stellar collisions that defy our current models. Each new finding will not only add to our catalogue of cosmic wonders, but will also deepen our understanding of our own place in the galaxy, reminding us that our single, tranquil sun is just one of countless ways a star can choose to live its life. This exploration underscores a beautiful truth about astronomy. The universe is not just stranger than we imagine, but stranger than we can imagine. These systems, with their complex dances and breathtaking violence, are a testament to that infinite creativity. So the next time you look up at the night sky, remember that hidden in the darkness are families of stars living out dramas of gravitational harmony and chaos on a scale we are only beginning to comprehend. If you've enjoyed this journey to the frontiers of stellar science, be sure to like this video and subscribe for more deep dives into the cosmos. And we'd love to hear from you in the comments. What's the most fascinating or wildest star system you've ever come across?